Sir, is the exam going to be MCQs or descriptive?
I really don't know about this because you can just drop an email to the instructor or write something on the discussion forum. Uh,
Sure, sir.
yeah.
Where is the discussion forum?
I guess it's on the NPTEL. You have an NPTEL account, right?
Yeah.
Probably you can find it somewhere because I could find it, so probably you can also find it. Uh, uh, Let me check once. Wait.
Oh, found it. It's called Q&A.
Yeah. Exactly. You can write something there and someone will reply.
Sure, sir.
Okay, so let's start. Yeah, so welcome to the second half of the NPTEL MA106 course. I am Shubhajit and I'm a PhD student at the Department of Mathematics IISc. So, as we keep doing every week, we'll solve problems based on the content of week 7 and just a small recap of what actually has been achieved this week. So, what all did you learn this week? So, you learned about the. So, in this week, you saw, uh, I would say, a refined version of the adjoint functor theorem, or rather of an, let's say, namely the special adjoint functor theorem. So, what is it about, or what does it essentially say? It says that let G be a functor from a category B into a category A, where P and A are locally small, and assume that B is complete, well powered, and has a co-generating set, or rather a co-separating set. I mean, it's the same. A co-generator is the same as a co-separator, and a co-generating set is the same as a co-separating set. Then G has a right adjoint functor if and only if G preserves limits. Okay. Yeah. So you also saw what these terms mean. I'm sorry. Uh, what does well powered mean, and what does having a co-separating set mean? So take a category C, let A be any object in C. Then what we want to do is we want to category theoretically capture sub-objects of an object. So for example, subgroups of a group or subsets of a set. So the idea to do that would essentially be looking at monomorphisms going into A. But then again, I mean, there could be two different monomorphisms going into A, but the domains can be, I mean, one might factor through, I mean, each of them might factor through the other one, right? So in which case we'll say that those two sub objects are the same. What I mean is, for example, suppose you take a set 1 2 3. If I want to define a sub object or a subset of 1 2 3 as some monomorphism going into this from some set S, let's say 1 2. So a monomorphism in the category of sets is exactly a map which is injective. So this is an injective map, and then again I would say that, let's say, from A to B to 1 to 3 you take this injective map sending A to 1 and B to 2, let's say. Then these two both are sub-objects of 1 to 3, but they are essentially the same, right? So what we want to do is we want to capture sub-objects in such a way that two sub-objects will be different if they are, I mean, if one doesn't factor through the other, if one of them doesn't factor through the in the, or very roughly speaking, we'll say two sub-objects are different if they are not isomorphic. So the idea, or the precise thing that I want to get at is this, that so take omega A to be the class of monos in the category C with target A. So what I want to do is I want to put an equivalence relation on this, right? So what is our equivalence relation? So suppose you take a mono A1 to A and you take a mono A2 to A. I'll say that two such monos are equivalent if and only if they factor through each other. In the lectures, probably first a pre-order relation has been introduced on the class omega A, and the pre-order relation is A1 will be less than equal to A2 if A1 factors through A2, or rather the map with domain A1 factors to the map with domain A2. That is a pre-order relation. What we want to do is turn this into a partial order, and the usual way of doing this is to look at a quotient of this class modulo this intersection less than equal to intersection greater than equal to relation. So what the equivalence relation is essentially is this, that two monomorphisms are equivalent if and only if they factor through each other. So by which I of course mean that is, so you have A1 to A and you have A2 to A. This is M1, this arrow is M2. So there should exist an arrow from A1 to A2, some arrow making this commute, and at the same time, since M2 should factor through M1, that means M2 can be written as a composition of some arrow, M2 can be written as a composition of some arrow from A2 to A1 composed with and M1. Yeah, so if there exists arrows in opposite directions making this commute. Now you can check that each dashed arrow or dotted arrow is actually an isomorphism. In fact, they are mutual inverses of each other. So you can essentially reformulate the equivalence relation by saying that M1 is equivalent to M2 if there is some isomorphism from A1 to A2 making the obvious triangle commute. So the point is that this is an equivalence relation. So tilde is an equivalence relation. On the class omega A, there could be a large amount of maps going into A which are monomorphisms, and what you do is you look at the quotient omega A mod tilde. So you consider omega A mod tilde. Now each equivalence class. Now we have essentially identified equivalent subobjects. So now each equivalence class is called a subobject of it. So for instance, as in our example, 1, 2 and AB together with those two specific monomorphisms are considered to be the same subobject. Okay, so this is the idea. So for example, in sets, since isomorphisms are essentially about cardinalities, so two sets are isomorphic if and only if they are as objects in the category of sets, if and only if they have the same cardinality. So classifying subobjects of, let's say, a finite set essentially reduces to classifying uh, subsets of A up to cardinality. That's all. Yeah. So now C is called well ordered. Well ordered. The category C will be called well ordered if each class omega A over tilde is actually a set. So each object should have a set of subobjects, or the class of subobjects of any object should be a set. Then the category C is called well ordered. This is one of the conditions in the statement of the special adjoint functor theorem. Moreover, what you should have is a co-separating set, which I am sure you can now figure out. Of course, you have seen the definition this week. You have also seen what a separating object is and what a separating set is. Just dualize it. So a family or a set xi ini of objects in a category C is called co-separating if for any two distinct arrows, parallel arrows A to B. So let's say this is F, let's say this is G, they are different. There exists some I in I together with an arrow B to xi such that the compositions are different. So A to B, F, G, B to xi are distinct. In other words, you can, if two maps are distinct, the distinctness can be detected by some object in your set xi. So this is the idea of a co-separating set or a set of co-separators. Okay, so under these conditions, that special adjoint functor theorem says that G has a right adjoint if and only if G preserves, G has a left adjoint if and only if G preserves limits. So this is the statement of the special adjoint functor theorem. You saw proof of this in the lectures, and you can also prove it using the general adjoint functor theorem by actually showing that for every object A in A, what the co-slice category over G, I mean A over G, has a weakly initial set, or what you call a solution set. So, and one more thing is the motivation actually comes from stone check compactification. I'm sure the lecturer has mentioned this. Which is a very standard functorial process in topology. Of turning a space into a compact house of space. Okay. What else did you study this week? You studied something called filtered colimits. So, what is a filtered colimit? A filtered colimit is a colimit of some diagram whose shape category is filtered, And what is a filtered category? A category is, let's say J is called filtered if for every finite category I, every diagram from I to J uh, has a cocone on it. Uh, or in simpler terms, what we mean is, so a category J will be called filtered if for every pair of objects, let's say J, J prime in J, there is some J double prime object in J together with arrows J to J double prime and J prime to J double prime. And moreover, if you take two parallel arrows J to J prime, let's say any two parallel arrows, there will exist some, let's say J0 together with an arrow J prime to J0 such that these composites are equal. So that's the definition of filtered colimits, and turns out that filtered colimits are really one of the most powerful kinds of colimits. They are colimits and they are very powerful or specific. I mean, they are the most useful ways of building objects out of simpler objects. Um, for instance, every set is a filtered colimit of its finite subsets. Every group is a filtered colimit of its finitely uh, okay, this might not be actually a good example. Every because we have to prove some things, but let's say every vector space is a filtered colimit of its finite dimensional subspaces, or every module is a filtered colimit of its finitely generated submodules, etc., etc. So you studied filtered colimits, and then you studied the notion of a locally finitely presentable category, which is a locally small category which is co-complete, has a, okay, you also, yeah, you also studied finitely presented objects which are sometimes also called compact objects of a category. So an object C in a category C is called finitely presented or compact if homing out of C actually commutes with filtered colimit. So in other words, if this functor, this co-representable functor co-represented by C from C to set preserves filtered colimits. Sometimes this is also referred to as a finitary functor. I'm sure the lecturer has mentioned all these things. And so you studied finitely presented objects, and then you studied the notion of an LFP category, locally finitely presentable category, by which one means a category which is locally small, co-complete, has a set worth of isomorphism class of finitely presented objects. So if you look at all the finitely presented objects and I mean look at the class of all finitely presented objects and mod it out modulo isomorphism, then that quotient must be a set. So you have a set worth of finitely presented objects, and in other words, there is only a set of isomorphism classes of finitely presented objects. And moreover, the most important one is that every object of your category should be a filtered colimit of finitely presented objects. And so this is the idea of a locally finitely presentable category. One of the most simplest examples is the category of sets. And you can in fact generalize this definition to, instead of taking finite, you can replace it by any cardinal, let's say alpha. So you can talk about alpha filtered colimits, which are colimits of diagrams in which the shape category is alpha filtered, by which I mean, so a category J will be alpha filtered if for every category I whose such that the cardinality of the arrows in I is cardinality of the set of arrows in I is strictly smaller than alpha. If you take a functor I to J, that should have a cocone. So you can replace finite by alpha. So finite means smaller than aleph 0, right? The countable cardinal. Alpha is some cardinal which replaces LF0. So you look at you look at everything smaller, strictly smaller than alpha. You can talk about alpha filtered colimits. You can talk about alpha presentable objects, and you can talk about locally alpha presentable category, etc., etc. So you can suitably generalize this definition. But yeah, we'll only stick with finitely presented objects and locally finitely presented categories. Okay, and you also saw something which is not directly a part of the um, exams, or rather the course, but you saw something called, I won't write this, but Gabriel-Ulmer duality, right? So we won't discuss it, but yeah, we'll stop here. This is all that I wanted to say this week. I mean, in the recap session. So yeah. So having seen all these things, let's quickly jump to the problems. Okay. So we'll solve only 3 problems this week, and let's start. Oh, okay, I forgot to mention something else. You also saw something very important, which will actually be solving as part of our exercise, that in any category, or rather you saw the general notion of limits or co-limits commuting. What it means for a particular co-limit, let's say, to commute with, co-limit of a particular shape to commute with, let's say, limit of a particular shape. Co-limit of, um, yeah. So notion of co-limits commuting with co-limits. What does this essentially mean? So for example, co-limits of of shape I commuting with limits of shape J, let's say. So the idea was basically you take a functor d I cross J to some category C, and there are canonical isomorphisms. So you look at the functor category from I cross J to C. There is an isomorphism from this to the functor category from I to the functor category from J to C, right? This actually happens because there is an adjunction for, if you look at cat and cat, then there are 2 functors that one can think of. For example, for J some category, you can look at bar cross J. This is a functor taking product with the category J, and there is some functor which is J comma gap, which sends every category C to the functor category from J to set. It turns out that there is an adjunction here as well, which sort of says that, you will see this sometime, which sort of says that the category cat is actually Cartesian closed, and it turns out that this J comma gap, this functor actually behaves like a Hom, except that usual Homs always map into sets. This Hom maps into cat. This is a category itself. For every C, this J comma C is itself a category. So this is like an internal Hom from J to C. Yeah, and there is an isomorphism as well from J to I comma C. So you can ask this question, that suppose you take a functor D from I cross J to C. You can look at this functor, let's say D upper dot from I to J comma C, and you can look at this functor, let's say D lower dot from J to I comma C. Let's say we are focusing on limits for the time being. Now we can compute limits here in various different ways. For instance, we can look at this functor, compute the limit of this, right? So we can look at limit I D upper dot. This by definition will be an object in the functor category from J to C. So this will be a diagram itself of shape J. Again we can take its limit, right? So we can look at limit J, limit I D upper dot. Or what one can do is look at limit j d lower dot. This will be an object in the functor category from I to C. So again we can take the limit over I. This will again be an object of C. Or we could directly take the limit of this functor I cross j d. This will be an object in C. The theorem says, or rather something probably which you should prove by yourself, is that if suppose that all these limits exist, so suppose that this limit exists, and suppose that this limit exists, and suppose that this limit also exists, I mean this exists and this exists, then in that case this limit will also exist, and there is actually a canonical there are canonical isomorphisms. So if you ignore this for the time being, what this portion says is essentially that limits are commuting with limits, and this is true in general in every category, that limits always commute with limits. Dually, co-limits commute with co-limits. If the appropriate limits exist, let's put it this way. So by this I mean this limit, and then this limit, and then this limit. Yeah. If these appropriate limits exist, then this happens. So so what you can say is that if suppose that if you take a category C, and suppose that C has limits of shape I for some small category I, and it has limits of shape J for some small category J, then it will have limits of shape I cross J as well. Okay. Dually, co-limits commute with co-limits. This is true in every category, and this is sometimes jokingly called the Fubini's theorem. So if you are from an analysis background or mathematics background, you have heard of Fubini's theorem, which says that under certain conditions integrals can be interchanged with each other. Okay, and the idea is that co-limits are thought of as some kind of sums. So co-limits commute with co-limits essentially means that sums sometimes commute, sums commute with sums, which is exactly the idea of Fubini's theorem, except that in analysis you require conditions. In category theory, this is always the case. This is always true. Okay. Okay, so let's start solving problems one by one. Okay, so assume without proof. So we'll assume this statement, and we won't actually be looking into the details of this. What we'll do is we'll assume without proof that a locally finitely presentable category is always well co-powered. So we know what well powered is. That is a yeah.
I couldn't hear from Fubini's theorem.
Oh, okay. I'll repeat it once again. So what I'm saying is that limits commute with limits. This is always true in every category, and dually one can say that co-limits commute with co-limits. You can prove this. Limits will always commute with limits. Dually, co-limits will therefore always commute with co-limits. This is true in every category. What is not true in general is that co-limits might not commute with limits. So co-limits of some particular shape I might not commute with limits in a category. It turns out that in the category of sets, filtered co-limits commute with finite limits, and not only so, in fact, if co-limits of a particular shape commute with all finite limits in the category of sets, then what you can show is that that shape category must itself be filtered, which is a very, very, very powerful statement. But in general, co-limits don't commute with limits, but in every category, limits will always commute with limits, co-limits will always commute with co-limits. What I'm saying is that this theorem is sometimes jokingly called the Fubini's theorem, because in analysis, Fubini's theorem is a theorem which says that under certain conditions two integrals commute. So if you have integral a and integral b, then you can actually write this as integral b integral a, integral over b integral over a, etc., etc. I'm not an analyst, so I don't know exactly what the exact conditions, but it says that under certain conditions this holds. Now colimits are thought of as sums. Okay, the idea is that colimits are sums. Thought of as sums. So, and integrals are like generalized sums, etc. That is why, since colimits commute with colimits, what this means is that this is like Fubini's theorem only, except you don't need any conditions. This is true in general. That is why it's called Fubini's theorem. In fact, there are certain special kinds of colimits which are called coends, which are usually denoted by an integral sign. Some integral, so coend of some specific functor, coend of some functor from C of cross C to, let's say, some category X, etc. It's a very special kind of colimit, and this result is also true for coends as well. That is, coends commute with coends, so it sort of exactly looks like Fubini's theorem. Yeah, this is all that I wanted to say or was saying. Can be thought of as sums. Colimits can be thought of as sums. Okay, yeah, enough of imprecise words, I would say. Let's move on with the problems. Okay, so for this problem, we'll assume without proof that a locally finitely presentable category is well co-powered. Okay, you have seen what the definition of well powered means. Means that every object A, for every object A, the class of all sub-objects of A is a set. So the dual notion, when you dualize sub-objects, so sub-objects are given by monomorphisms going into A. So the dual notion would be epimorphisms out of A, which are essentially the same as quotient objects. So you look at equivalence class of epimorphisms out of A with the dual equivalence relation. That if you look at the quotient, each equivalence class is called a quotient object of it, and a category will be well co-powered if for every object A, the class of all quotient objects of A is a set. So we'll assume without proof, this is a non-trivial theorem, we'll assume without proof that a locally finitely presentable category is well co-powered. Okay. What we want to show is that if C is a locally finitely presentable category, then any continuous functor from C up to set is representable. And of course, as understood here, we wish to apply the special adjoint functor theorem. So yeah, let's do it. So we wish to apply the special adjoint functor theorem. Okay, so what are the conditions of S.A.F.T? We want to apply the special adjoint functor theorem to this to a particular functor C up to set. So we first fix a functor, let u from, or let's say let g from C up to set is representable. I mean, sorry, be a functor, be a continuous functor. Okay, we want to apply the special adjoint functor theorem. So what are the conditions that we need? So hypothesis, or we need, so hypothesis of S.A.F.T. Firstly, so we claim that this functor G actually has a G should have a left adjoint. That is what we claim. So hypotheses are, firstly, we want C to be C op to be locally small, which we already have because C is locally finitely presentable. By definition, C is locally small, so C op will be locally small. Second condition that we need is that set should be locally small, which we already have. We already know that set is locally small. If you take two sets A and B, then the set of all mappings from A to B is itself a set. What we want next is that C op should be complete. Again, since C is locally finitely presentable, one of the things that are required in the definition of locally finitely presentable categories is co-completeness. So C is co-complete means that C op is complete. It has all small limits. What else we need? C op should be well powered. Again, we have this based on this assumption, based on the fact that we know that a locally finitely presentable category is well co-powered. We assume this without proof. So C is locally finitely presentable means that C is well co-powered. So therefore C op, the opposite category, should be well powered. So we already have this for free. What we want is C op should have a co-separating family of objects, or rather a family of co-separators. This is not given to us. We need to show that this holds. Okay. So the idea would now be to obtain a set of objects which are co-separators. Okay. So how do you obtain a co-separating family? So I'll put a question mark here. So want a co-separating family of objects. So observe that C op, observe that the category C is locally finitely presentable, right? So obtaining a co-separating family of objects for C op is the same by duality. It's the same. Formulating the dual notion or dual statement would mean that is to obtain a separating family of objects for C. Yeah. So that is. So I'll write it properly. So want a co-separating family of objects for C op. That is equivalently want a separating family of objects for C. So how do you obtain a separating family of objects for C? So observe that C is locally finitely presentable, which means that there is, if you look at the class of all finitely presented objects, take a quotient of it modulo the equivalence relation of isomorphism, then the quotient is a set. In other words, there is a set. It has a set worth of finitely isomorphism class of finitely presented objects. So let C.F.P, let's say, be the full subcategory. So this is just formally, so we are just formally writing things down, that's all. So let C.F.P be the full subcategory. So full means that the inclusion, the functor from the subcategory into C is a full functor. So let C.F.P be the full subcategory of C, determined by the finitely presented objects. So what our assumption that C is LFP in particular implies is that CFP, the subcategory, is actually essentially small. In other words, it has a small skeleton, or in other words, you can say that it is equivalent to a small category. Just look at the full subcategory of CFP itself, consisting of exactly one object. look at a full subcategory of CFP consisting of exactly one object from each isomorphism class of objects. So take CFP. So by assumption, CFP is essentially small. Okay. Yeah. So let xi I in I be a set of representatives from each isomorphism class. Let's write it this way. Let D be a skeleton. So it will be small of CFP. That is, you are picking exactly one object from each isomorphism class of objects in CFP. Look at the corresponding full subcategory, that is your skeleton. That is the definition of skeleton of a category. What our assumption of C being LFP implies that D is a small category. Okay. So claim is that, so we note that D is small, the category D is small. So claim is that OBD, the class of objects of D, which is actually a set, so I can say the set of objects of D is a separating set. For C, and the proof is very easy. It follows in 2 lines actually. So why exactly? Because let A to B, F, G be 2 distinct arrows in C. Okay. So by definition, again by the fact that since C is LFP, every object is a filtered colimit of finitely presented objects. A can be written as a filtered colimit, or let's write it like this. A is isomorphic to some, so to the colimit, let's say colimit over I of some diagram D, where D from I into I mean C is a diagram, or D from I into not C exactly, D from I into D actually. I mean, it's a diagram of finitely presented objects. So D is actually a functor from I into D, is a diagram, and I is filtered, right? So assume how should we say this? So if, so what you have is 2 maps, right? So you have the colimit I D to B. You have 2 maps F and G. Okay. So if so what you have is for every I, so for every I in I, you have a map from DI into the canonical co-projection associated to the colimit, this, and you have these two maps F, G, B. The point is that there exists, yeah, or for every I, take the composition, take this composition, where the first map is actually the structure map associated to the colimit. The canonical map for di for I associated to the colimit. The colimit is always a cocone, right, over the diagram D. So you always have a map from every. I mean, you always have a map. You have a map from di to the colimit for every I. So you take this composition. Now the point is that if for every I if um, if composed with the structure map is G composed with the structure map. What does this mean? So look at this picture. You have this diagram D. There are objects. There are arrows as well. Let's say etc. etc. This is your colimit. And suppose this is your object B. You have two maps F, G. If you compose all these maps with F, you obtain a cocone on the diagram D with vertex B. And if you compose all these maps with G, you obtain a cocone on the diagram with vertex B again. Now if the compositions are equal, that means that the two cocones are equal, right? Now by the universal property of colimits, this single cocone, which is an arbitrary cocone actually, that this single cocone will be, what should I say, has to factor uniquely through the colimit cocone, right? So what this means is that there should exist a unique map from the colimit to B that makes all triangles commute, all small triangles commute appropriately. Now we see that both F and G make the triangles commute, which is a contradiction unless F equal to G, which is a contradiction because F was assumed to be different from G, and that is actually the proof. So let's write it properly just to not confuse. So yeah, so let's have some notation instead. Oopsie. Yeah, let's have some notation. Let's say we call this structure map to be mu I, okay, where mu I is the structure map associated to the colimit. So this is, let's say, di, this is mu I. Let's say this is di prime, this is mu I prime. Suppose this is di double prime, etc. This is mu I double prime, etc. etc. Now if for every I in I, F composed with mu I is equal to G composed with mu I, then B comma di to B. So is it F? Yeah. So F composed with mu I equal to G composed with mu I. This, where I is in I, is a cocone. it's a I mean it's regardless of if you compose with F. So if you compose with F, you have a cocon. If you compose with G, you have a cocon. But it turns out if we assume F compose mu I is G compose mu I for every I in I, then the cocons are the same. So you get the same cocon. So this is a cocon on the diagram D, right? By the universal property of colimits, this cocon B comma di to be F compose mu I equal to G compose mu I in I, is, I mean, factors uniquely excuse my handwriting, yeah, factors uniquely through the colimit cocon, factors uniquely through the colimit. So there should exist a unique map from the colimit object to B such that F compose mu I, so so in other words there should exist, so there exists a unique map H from the colimit I D to B such that uh, H composed with mu I should be equal to each individual arm of the colimit, which in this case is F composed mu I, this map, which we also know is equal to G composed mu I by our assumption, right? Now for every I, yeah, for every I in I. Now observe that taking H equal to F makes this equation true. Taking H equal to G at the same time also makes this equation true. So F is equal to G, right? Taking F also, I mean F is a map which makes every such small triangle commute, or which makes this equation true, right? This equation is true for H equal to F. This equation is also true for H equal to G. G compose mu I is F compose mu I, because F compose mu I was assumed to be G compose mu I for every I in I. So F has to be equal to G because H should be the only map, right, which makes this happen. Both F and G make this happen. That means F has to be equal to G, right? And this is a contradiction because we assumed that F was not equal to G. In other words, what you can say is that since what does the colimit represent? It represents a functor. It represents the cocon functor, right? On the diagram D, cocon dash comma D comma dash. There is a natural isomorphism from this functor to our category is C, right? Yeah, to this. Did I put the sign of the colimit? Oops. This is the sign of the colimit. I don't know why I'm right. Yeah. I hope I have written each one of them correctly. Yeah. So limit I in I, or limit I, let's say, it doesn't really matter. It's limit ID gap, right? So in other words, if you take this is just a smaller argument of what we just wrote from here onwards. What we just wrote till now, just writing it in 2 lines. So In particular, this is, you have a natural isomorphism, so each component is an isomorphism. So that is a bijection from this set to, so there exists a bijection from this set to C I D B, right? So the point is, you look at this object, this is a coconon B, right? So this thing is here, right? So you should get a unique map from this to this, because you have an isomorphism. For every cocon there should be a unique map, right? But it turns out that both F and G actually map to the same cocon under the inverse of this map, which is a, which should imply that F should be equal to G, because you have a bijection, right? Just look at the opposite direction map, the inverse map. Right. So let's put it in brackets. Just a smaller way of saying this. This thing is here. This is a cocon on the diagram D with vertex B. Both F and G map to the same thing. So this is a bijection, so F has to be equal to G. Okay, anyways, so since F was not assumed to be G, right? Since F was different from G, so therefore by contrapositivity we can say there exists some I in I such that F composed with mu I is not equal to G composed with mu I, and this is exactly what we needed, right? What we needed was, we took two maps, right? We took two arbitrary maps A to B, F, G, which are distinct. What we needed was, we claimed that our OBD was actually a a separator, separating family. So what we actually needed was some object xi of OBD together with a map xi to A, such that the compositions are also different, right? And we can just look at di, right? Di, which is finitely presented, D was a diagram into the category D, where D was actually a skeleton of CFP. I mean, D consisted of finitely presented objects with exactly one finitely presented object from each isomorphism class of objects of CFP. So yeah, there you have it, right? So let's just say that Di to A to B, FG, Di is here, Di is in OBD, and this compositions, these two composites are distinct. Now since A, B, F, G are arbitrary, so OBD is a co-separating family of objects. Separating family of objects for C. Very simple, very simple. What we essentially did was just write A as a filtered colimit. You didn't even need the filteredness assumption here. You wrote it as a colimit and use the universal property of colimits to deduce that there is some coprojection from Di to A associated to the colimit, which actually does the job. So OBD is a separating family, separating set of objects for C. So OBD, the same objects, but now considered in the opposite category, is a co-separating family of objects for C op. So there you go. The last condition has now been verified. We have also verified that C of has a co-separating family. So all conditions are verified. The special adjoint functor theorem says that G, the functor G, will have a left adjoint if and only if it preserves limits. We already assume that our functor G is continuous, that is, it preserves limits. So that means, so since G is continuous, that is, preserves limits, so G has a left adjoint F from set to C. F from set to C op. G is from C op to set, right? Yeah. So the left adjoint should be in the opposite direction, that is from set to C op. And now we are done. We wanted to show that G is representable. Having a left adjoint actually means that G is representable. So let's write down what we have. Since set C op, this is F. You have a functor in the opposite direction, G. F is left adjoint to G. So C op of Fs comma C for some object C and some set S is in bijection with set of S comma GC naturally in S in set comma C in C op. So C op in particular of F1 comma C is in bijection with set of 1 comma GC, where 1 denotes the terminal set, the singleton set with exactly one element, naturally in C op, right? So, and moreover, you know that this is isomorphic to GC itself. Maps from the singleton set to a set are in bijection with the elements of the set, right? Because you know that the identity functor on set is naturally isomorphic to set 1 comma dash. 1 is a generator. The terminal object is a generator of the category of sets, and in fact you have an isomorphism. Set is representably concrete. Sometimes also people say this, but anyways, there is a natural isomorphism from this functor to this functor. So there will be a natural isomorphism if you compose with G, from G to, let's say, from G to set of 1 comma G, which is exactly this. And this is, since this isomorphism is natural, it means that this isomorphism is natural in the variable. I mean, if you take GC, if you take in particular GC to set 1 comma GC, this will be natural in the variable C, which is exactly what we wanted. So that is why we can write, so this is isomorphic to this, which is isomorphic to this, naturally in C op. Okay. The reason is this: the identity functor on set is naturally isomorphic to set 1 comma f. Yeah. So this holds. So, and that essentially means that the functor C of f1 comma dash is which is also the same as C of dash comma f1, just taking opposite category, is isomorphic to G. Okay. Which means that the functor G is representable and it's represented by the object f1. So in other words, elements of the set GC for some object C are the same as maps from C to f1. So G is representable, and in fact the representing object is f1. Yeah, so we are done. This is what we wanted to show. Okay, any questions, Srisha?
No, sir.
Let's move on to the next problem. It will be a bit simpler. So the question asks, so we know that limits commute with limits in every category. Limits always commute with limits. So we want to deduce that if you take a family of monomorphisms in a category, then if you take the product map from product AI to product BI, this will also be a monomorphism. So let me explain how do you get this map actually. So you have AI to BI, FI, right? So that means you have a map from product AI I in I to AI to, let's say, AJ to FJ to BJ, right? For each J in I. This is your projection. We are doing everything in an abstract category C. Okay. And hence by universal property of products. So think of this as some arbitrary object. From this arbitrary object to each BJ you have a map. The product of BJ's is the universal one with this property. So by universal property of the product BJ or product BI, let's say I in I, together with the projection maps BI to BJ, J in I, right? By the universal property of the product, there exists a unique map which we are calling product FI, I in I, from product AI, I in I into product BI, I in I, such that, of course, the uniqueness is subject to the commutativity of diagrams like this. So product AI, I in I to AI, or let's say AJ to BJ. This is your map from product AI to BJ, FJ projection. And this is your unique map product FI, I in I, from product AI into product BI, I in I. And this is the universal map projection. This commutes for each J in capital J. So this is how you exactly obtain. So I was just trying to define product of FIs, what exactly it is. So what we want to show now is that if we are given this data that this FJ arrow is a monomorphism, we want to show that this product map that we FJ is a monomorphism for every J in J. What we want to show is that this product map is a monomorphism. Now you can show this directly using the definition of monomorphisms. That won't require any kind of result like limits commute with limits. So so let's put this as an exercise. So check that if J is a mono for every J I, then product of FIs, this map is also a mono. Directly, check directly without using any kind of property. This can be done very easily. You just look at product FJ J in I, product FI J in I, whatever, product AI, product BI. Assume that there are two maps P and Q from some object X to this, such that these compositions are equal. You need to show that P should be equal to Q. Just project it down to BI or some to the BJs. You know that this also factors like projection with Fi, and use whatever you can. I mean, this will follow from the universal property of products. But what we want here is to use our Fubini's theorem, limits commute with limits, and what we exactly do is this. So, and I mean, the main idea behind posing this question is actually the solution, not the question itself. So you learn a number of things from this. That is why we we are we have posed this question. So this is a very important property, a characterizing property of monomorphisms, that a morphism if from A to B, I hope I didn't use A anywhere or B anywhere. Yeah. Oops. Yeah. A to B in a category C is a monomorphism if and only if the following square, commutative square, is a pullback. Very simple. So what you do is you take A to be F, you take A to be F, you take A to A identity on A to A identity on A. This certainly commutes. This square should be a pullback square. If F is a monomorphism, this square is a pullback square. Conversely, if this square is a pullback square, then F is a monomorphism. So in other words, F is a monomorphism if and only if its pullback along itself consists of identities. That is, if and only if its kernel pair consists of identities, up to isomorphism, of course. So check this. Very easy to see, very easy to check, but do verify this. And now we use our property. So pullbacks are monomorphisms themselves. So what you have essentially is this, right? You have, so coming back to the problem, so what does the statement pullbacks commute with products mean? It essentially means that if you take any diagram D, I cross J into some category C, where your shape category I looks like this, let's say, and your shape category J is a discrete category. Okay, we sort of, yeah, since we have already used the notation I is a discrete category. Think of, so I is a set, think of it as a discrete category. The same objects as the elements of the set, just only identity arrows. And J is this category, the shape for pullbacks. So looking at a functor from I cross J to C exactly means you have a diagram in C of this shape I cross J. That is, the diagram will look something like this, right? So object, 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 arrow, arrow, arrow. For every I in I, you have a diagram like this. Consider the, so this is for I prime in I, let's say, and so on. You have a span diagram like this for every I in I. So look at them all together. This is how your diagram looks in C. What saying that pullbacks commute with limits essentially means is that if in our previous note, okay, so it means that limit I in I, limit J in J, dij is equal to limit J, limit I in I, limit J in J, dij. So what does the first thing say? It says that if you look at the diagram D, for a fixed J in J, right? If you look at the limit of dij's, right? So what does that mean? It means that, so J here is fixed. So let's say you fix this object. So what you have is a diagram of shape I in C consisting of this circled objects, right? Take the limit, which will essentially be the product of all these objects, right? And so on. And then take the limit over J. So for this object, you have the product of these objects. For this object, you have the product of this objects, and so on. For this object, you have the product of these objects, and so on. So what you essentially have is an object, I mean the product object together with the product map and the product object. Take the pullback of this. Let's say P is the pullback. This P will be the same, will be canonically isomorphic or naturally isomorphic to, if instead of taking products and then pullbacks, if instead you first take, this is what is conveyed by the second line, instead you first take pullback of this, then take the pullback of this, the pullback of each individual cospan you take, and then take the product of the pullbacks. Those two will be the same. Okay, so let's have a colorful picture for this. I'll just write a picture and nothing else. So um, let's say, so D looks like, so the diagram D looks like, so this is a diagram in C, it looks something like this. So you have an object, you have another object, you have another object, and so on. And you have, so this is for, so let's this object, I don't know if coloring this would be a good idea. Okay, let's not color it. So you have objects like this, you have objects like this. Okay, and you have objects like this, a different color, this one let's say. And you have arrows. So for this is for let's say I in I. This is for the index I prime in I. This is for the index I double prime in I, and so on. Okay. So you have a cospan, you have a cospan, you have a cospan, and so on. Collectively, you look at this picture. So this line conveys oopsie. This line essentially conveys is that you can individually take the pullbacks of each of these cospans, right? And then obtain the product, or you can obtain the product of the individual things, right? So conveys that, let's write it nicely. So product of this, okay, let's product of the red objects, let's say, yeah, product of the red objects I in I, then product of the green objects, product I in I of the green objects, and the product of the blue objects I in I of the blue objects, right? And you have, of course, oops, and you of course have maps. So you have a map which is the product map of each individual map. So this is, let's say, I mean we have used fi, let's say this is hi, let's say this is hi prime, and so on. So this is product of hi's actually, and hi double prime, etc, etc. This is, let's say, gi prime, gi double prime. This is, you have a map from this to this which is product of gi's, I in I in I. Okay. Now if you obtain the pullback of this, taking the pullback here, is the same, this pullback is the same as first obtaining the pullbacks of each of them and then taking the product. So let's write it. Let's say this is P. What this says is that P is the same. What this line says is that P is canonically isomorphic, naturally isomorphic, morphic to, you obtain pullbacks, individual pullbacks. So let's, you take individual pullbacks. So pullback pi, pullback pi prime, pullback pi double prime, and so on, right? Is so P is naturally isomorphic to product of pi's, I in I, where each pi is the pullback of the corresponding cospan, right? So pi is the pullback here, pi prime is the pullback here, pi double prime is the pullback here, and so on. Okay, this is what the result says. P is naturally isomorphic to that. Now how do we use this actually for the purpose of our problem? What we are given, recall, is the family of monomorphisms fi, ai to bi, right? What we want to show is that product of fi is also a monomorphism. So in particular, this says that if in our language, in the language that we learned this week, in particular, if this says that if ai comma fi is a sub-object of bi, look at its equivalence class, then product ai comma product of fi, look at the equivalence class of that. I mean, even before equivalence class, product fi is a monomorphism. So product ai comma product fi, look at the equivalence class of that. That is that equivalence class is again a sub-object of product bi. This is what it says. So now for the problem, since fi's were given to be a pullback, so ai bi fi, I mean sorry, since fi's were given to be monomorphisms, each fi was a monomorphism, so this is a pullback square. Right. Again for I prime, ai prime, bi prime, ai prime, fi prime, fi prime, ai prime. This is one ai, by the way. This is one ai, by the way. This is one ai prime. This is one ai prime, right? This is a pullback again for ai double prime to bi double prime, fi double prime, ai double prime to bi double prime, fi double prime, ai double prime. This is 1 on ai double prime. This is 1 on ai double prime. This is a pullback, and so on, right? So what our result says is that taking the pullback of each of them individually and then obtaining the product is the same as taking the product and then obtaining the pullback. So result says product of AIs, right, is naturally isomorphic to, of course, together with the maps, together with the arms of the map is, or let's write it all together. So result says that AI, so if you take product of AIs, product of BIs, product of FI, I in I, of course, I in I, always I in I, product of AI, I in I. What the result says is that since each AIs were pullbacks, right? If you take the product of all these pullbacks, this will be the pullback of this diagram. So product of AI. So we didn't even need to check this. This follows directly from the result. This is 1 on product AI. Of course, if you since each of these individual maps was identity, right? So from the product to the product, you of course have the induced map is the identity again, and similarly for this map as well. Each of these individual maps were identities, right? So 1 product AI, right? I mean, yeah. I mean, I should write product 1 AI, but then again, it's the same. Result says that this is a pullback square. I mean, let's write it. Product of 1 AIs. Product of the maps 1 AIs. Yeah. Result says that this is a pullback square, and this again using the if and only if condition, that a morphism is a monomorphism if and only if the following square is a pullback. We know that this square is a pullback with the projections from the pullback given by the identities. So product AI, I in I to, yeah, let's not write this is a mono a priori, we need to verify that. Yeah. Product AI to product BI, I in I is a monomorphism. Using the characterization that we had of monomorphisms. Using pullbacks. So is this clear, by the way, Srisha?
Sure, sir.
Yeah.
Yes.
Yeah, I mean, I should say together with the maps. Induced arrows. The arms of the pullback. Okay, so this finishes our problem. Fine, let's solve our last problem and then stop for today. So the result says that suppose C is a locally small complete well-powered category with a co-generating set, lots of conditions, but we have already seen all this. This is precisely the hypothesis of the special adjoint functor theorem. So suppose that C is actually a locally small category which is complete, is well-powered and has a co-generating set. Show that C is co-complete as well. This is very interesting. Completeness of a category with certain conditions actually implies co-completeness as well. So to do this, we recall some things. For any small category C, consider the diagonal functor, or rather recall the diagonal functor. We have seen this functor previously, delta from C into C power, sorry, for any small category J, C is given to us, C power J. Consider this, I mean this is just the functor category from J to C. Okay, we consider this diagonal functor. What does this actually do? It maps an object C of C to the constant functor with value C. So delta C is your functor from J to C, which maps every object little j to the object C and maps, so maps J prime also to object C and maps an arrow to the identity arrow. This is your delta C. So delta is your diagonal functor. We already had this functor, and I'm sure you have seen this, that suppose that your category C has, let's say, co-limits of shape J, then this functor actually has a left adjoint which is given by the co-limit functor, right? Conversely, if this functor has a left adjoint, you can show that C has co-limits of shape J. This is actually part of a very general result concerning something called Kahn extensions in category theory, but let's just focus on this. So how do we write this? Yeah, so we know delta has a left adjoint if and only if C has co-limits of shape J. So what what would the left adjoint in that case? If C has co-limits of shape J, or if it has a left adjoint, the left adjoint is actually naturally isomorphic to this functor. So C to Cj, you already have the functor delta, and you have a left adjoint for this, which is obtained by taking co-limits of shape J. This is the left adjoint. So what does this do? This sends every object in C power J, that is a functor category from J to C. So D, if D is an object in C power J, D is a diagram of shape J in C, and D is getting mapped under this functor to the co-limit. Okay. This functor, this actually is this assignment is actually a functorial assignment, or is functorial in the sense that it extends to maps as well. So if you have a natural transformation from D to D prime, you will have a induced map from the co-limit of D to the co-limit of D prime, making certain things commute. Okay, and why is this left adjoint, by the way? Because C of any object, limit JD comma some object of C, let's say C. So D is a diagram here, C is an object here. Why is this set in bijection with why is there a natural bijection from this set to C power J D comma delta C? Delta is the right adjoint, right? Yeah, it's because an element here, that is an arrow from D to delta C, that is a natural transformation from D to delta C, is actually a cocone on D, right, with vertex C. And we know every cocone will factor through the universal cocone, which in this case exists because we assume C has co-limits of shape J. So that means there will exist a unique map from the co-limit to C, that is an element in this set, in this home set, right? So you have and this is a bijective map. This assignment of an arrow going to a cocone, to the corresponding composite cocone, is actually a bijection. This is just the property of co-limits, right? So this happens. Conversely, you can prove that, suppose you have a left adjoint, don't assume that this is limit J, assume that the left adjoint is F. You can show that it will have co-limits, C will have co-limits. Exactly, if D is a diagram of shape J, F of D, you can check, will be the co-limit, because it will have whatever F is, F of D will be given by this property, with instead of this you write F of D, right? So it says that maps from FD to C are in natural bijection with maps from D to delta C, right? that is cocones on diagram D with vertex C and in natural bijection with maps from FD to C, right? This you have a bijection. So for every C in C and for every D in C power j, you have a bijection from this home set to this home set naturally in C and in D. That essentially means that FD is just the colimit of the diagram D, right? Okay. So let me just write that this is actually a special case. This result is actually a special case of a very general result about Kahn extensions, something called Kahn extensions in category theory. We of course won't be seeing this, what Kahn extensions actually are, but yeah, just to make a note of this. Yeah. So we want to show that C is co-complete as well. We can use this result now, right? That is, we can show that for every small category J, we want to show that C has co-limits of shape J. We can just show that this functor delta has a left adjoint. And to do that, what we'll be using is our special adjoint functor theorem, right? And this is a one line because everything is given to you. So just observe. So we claim that for every small category J, delta from C to Cj, the diagonal functor has a left adjoint. So how do you show this? How do you show that delta actually has a left adjoint? So we wish to apply S.A.F.T, the special adjoint functor theorem. So recall the hypothesis. What we need is, firstly, C is locally small. Is it given to us? Yes, it is given to us. We need C power j is locally small. Is it given to us? No, it is not given to us. So let's put a question mark here. We need what else? We need C is well powered. Is it given to us? Yes, it is given to us. So let's put ticks. We need C has a co-generating set. Is it given to us? Yes. So let's put a big question mark here. We need C power j. I'm sorry, we need C should be complete. Is it given to us? Yes, it is given to us. So hypothesis of S.A.F.T. Finally, what we also need is delta should preserve limits, should be continuous. Delta should preserve limits. Let's say delta preserves limits. This is one of the conditions that we need. Is it given to us? No, delta we consider delta. Delta was itself not given. So delta preserves limits. Big question mark. We don't know yet. So two things we need to verify. C power j is locally small and delta preserves limits. Now why is C power j locally small? In other words, why? So if you fix two functors f and g from j to c, why is there a set worth of arrows from f to g in the functor category? That is, why is there a set worth of natural transformations from f to g? So we claim c power j is locally small. Each Hom set is actually a set. So fix f comma g from in c power j, both are functors from j to c. So want to show nat f comma g, the set of all natural transformations from f to g is a set. Of course, if f were, let's say, representable, then we could apply the Yoneda lemma in this case, right? Since c is locally small, we can apply the Yoneda lemma and say that suppose f is naturally isomorphic to functor represented by some object c, then this set nat c of c comma gap comma g, the set of the object of natural transformations, the set of natural transformations in this case from this to the representable functor represented by c to g are this is isomorphic to, that is, there is a bijection from this set to the set gc, right? Gc is a set by okay, I'm sorry, yeah, to make sense of representability, of course you need c to be set here, yeah, but yeah, in that case everything is trivial because in set is already co-complete. But still, if we want to go along this line of argument, so gc is a set now, and hence the set of the class of natural transformations from a representable to g is also a set. But f is a general functor, c is a generic abstract category, so we can't use Yoneda lemma really. So we want to show nat fj is a set, and what we do is we consider this map. From what to what? Nat f comma g, or let's say a mapping, I should say. But yeah, everything makes sense if you the word set, class, etc., everything makes sense if you fix universes and then do it. We have from beginning only we have made a clear distinction between what is a set and what is a proper class, not a set. That's a primitive so we have assumed that there is some distinction between them. So nat fg to product product j in j, c of fj comma gj, right? What is this map? Sends alpha to alpha only. So what does this do? The class alpha j. So alpha is a natural transformation from f to g, which means that alpha is exactly a family of arrows in C with exactly one arrow for every object j in the domain category or the source category. So alpha j, family of alpha j's. Each alpha j is from fj to gj. F applied on j to g applied on j, j in capital J. This is a family of arrows in C. So you send alpha to this. This is an injective assignment. This assignment is injective, obviously, because alpha is getting sent to itself only. In other words, if you take alpha and beta both from f to g and assume each alpha j is equal to beta j, which means that all the components of alpha and beta agree, which means that alpha and beta as natural transformations are equal, which is exactly what we wanted. So this assignment is injective, obviously. Right? Now C is locally small. This was given to us. So for each j, so implies for each j in j, cfj comma gj is a set, which implies, since j is a small category, class of all arrows in j is a set. So So since j is small, this implies that the product j in j, c of fj comma gj is also a set. Right? This is one of the axioms of ZFC. If you have a set index family of sets, if you take their product set, the product will also be a set. You can you can prove this using the axioms of ZFC. Oops. Yeah. Yeah. So now what we have is, this is a set. You have an injection of this into this. Certainly this can't be anything bigger than that. So when I say terms like bigger, smaller, etc., we are working in a particular model of set theory, assume all these things. So all these terms make sense. So nat fg is a set. Which is exactly what we wanted. So since f and g are arbitrary, so c power j is locally small. Did I use c or script c? Script c. Script c, power j is locally small. What else do we need? We need to verify that delta preserves limits. What is delta? Delta was a diagonal functor from c to c power j. So our final claim is this. This functor delta from c to c power j preserves limits. Observe that the category, by the way, observe that the category C was assumed to be complete, which means that the functor delta also has a right adjoint. We want to show that delta has a left adjoint, right? This is what we want. But since C is complete, delta also has a right adjoint, right? Which is obtained by taking limits, by considering the limit functor. Okay, so delta has a right adjoint means delta is itself a left adjoint, right? So what I'm trying to say is, you have c power j, you have delta, you have a functor from c power j to c, which is the limit functor, limit j. This exists because c has limits of shape j, and this is a right adjoint to this. So delta is itself a left adjoint. There is one adjunction like this, where the limit functor is the right adjoint and delta is the left adjoint. So delta preserves co-limits. We know this for free. What we are claiming here is that there will exist another functor, which is limit j, obtained by taking co-limits, which is left adjoint to this. So there is one more adjunction where delta is the right adjoint and this co-limit functor is the left adjoint. So to summarize, you have exactly two adjunctions here. Okay, one of the adjunctions is between the limit functor and delta, where limit functor is the right adjoint and delta is the left adjoint, and there is one more adjunction where delta is the right adjoint and there is one more adjunction between delta and the co-limit functor, right, where delta is the right adjoint and the co-limit functor is a left adjoint. Okay, we want to prove the existence of this, the co-limit functor. So let's keep this picture. Yeah, so delta is from c to c power j, preserves limits. So take a diagram D of some shape I in C. Okay, what we want to show is that, since C is complete, by the way, what we want to show is that if you take the limit of this diagram, and apply delta on that, then that should be naturally isomorphic to limit of delta of delta compose D, that is limit I in I delta of di, and that is obvious. So let's let's write it nicely. I mean, okay, observe that limit, or rather delta limit I di is isomorphic to limit I delta di. Okay, why is this, by the way? Because if the limit is L, right, so suppose you take this is your diagram D. Suppose L is a limit cone on this diagram. If you, so this is entirely in the category C. If you pass to the category C power G in terms of the functor delta, so now you have this composite diagram, which is delta composed D, and you take delta L. So here objects are di, di prime, di double prime together with arrows. Here objects are delta di, delta di prime, and so on, etc. And you have arrows, that is natural transformations. This will actually be the universal cocone. And why is that the case? Because take any arbitrary, universal cone on this diagram. Take any arbitrary cone B on this diagram together with natural transformations, B to this, B to that. Okay. Why is there a unique arrow from B to delta L making this commute? Because yeah, by the way, B is a functor. Wait a second, something is not correct. What is the issue? Okay, you don't need to do all these things. Yeah, it's not wrong. You can do it this way as well. But the point is, you're taking limits in a functor category, and they are computed object wise. So observe that this holds since limits in C power j are computed object wise. In other words, if you take limit, taking the limit of this delta di, this is supposed to be a functor from j to C. So this functor evaluated at an object j will exactly be limit I delta di applied on j, right, which is just limit I delta di of j is just di, right, and this is just L, right, and you can check that it takes arrows to identity arrows only. So the point here is this, that since limits in functor categories are computed object wise, so this functor is actually constant functor for each j in capital J. And you can check that it takes arrows to identities on L. That's all. Okay, so this is obvious now. So hence delta from C to C power j preserves limits. So we have already verified the last assumption as well, delta preserves limits. So by S.A.F.T, the functor delta from C to C power j has a left adjoint. Okay, hence C has By our result, C has co-limits of shape J. Since the category J is small arbitrary, so C is co-complete. It has co-limits of every shape, every small shape, so C is co-complete, and this is exactly what we wanted to prove. So just to record, we'll keep this picture. So there are two adjunctions here. Okay. Yeah, that's all. Any questions? Do you have any questions?
No, sir.
Okay. Let's stop then, I guess. You can send an email or write something up on the discussion forum to verify what exactly is going to be the pattern of the exam. But I'm pretty sure they won't just be MCQ problems, okay? Because you can already understand that from the assignments.
Sure, sir. Makes sense.
Yeah, okay. Okay, so see you next week. Bye bye.